January 27, 1986. Huntsville, Alabama. It was 9 o'clock at night. Outside, the temperature had dropped to 29 degrees Fahrenheit. One of the coldest nights Huntsville had recorded in years. Inside a conference room on the 14th floor of the Morton Thiokol building, a man named Roger Boisjoly was losing a fight he had already won on paper. He was 51 years old, a SEAL engineer. The kind of man who had spent 20 years understanding exactly what rubber does under pressure, under cold, under the specific stress conditions of a solid rocket booster traveling at 2,000 miles per hour. He was not a theorist. He was not someone who worked with models and projections and simulations. He worked with the actual physical reality of how materials behave when everything is trying to kill them. And on this night, he was telling a room full of executives and NASA managers that the Space Shuttle Challenger should not launch in the morning. Not should be delayed, not should be reviewed, should not launch. He had the data, he had the photographs, he had the documented erosion patterns from previous flights. He had 6 months of formal written warnings sitting in a filing cabinet with his name on them. He had everything except the one thing that ultimately decides these questions in large organizations. He did not have the authority to stop it. The phone line connecting Morton Thiokol in Utah to NASA's Marshall Space Flight Center in Huntsville had been open for hours. The argument had been going on so long that people had stopped arguing and started simply waiting for someone to give in. NASA managers were applying pressure. They needed a launch. There were schedules. There was visibility. There was a teacher on board, the first civilian in space, and the world was watching. And Roger Boisjoly was standing in front of a teleconference screen, showing photographs of O-ring erosion from previous cold weather launches, explaining in the precise technical language he had spent 2 decades developing exactly why the primary seal on the right solid rocket booster would fail if the temperature at launch was below 53 degrees Fahrenheit. The forecast for Cape Canaveral on the morning of January 28th was 29 degrees at launch time. 29 degrees. He had never asked them to take his word for it. He was showing them the physical evidence of what the cold did to the rubber. The erosion was real. The pattern was real. The correlation between temperature and seal performance was documented across multiple flights. This was not a theory. This was a forensic reconstruction of what had already happened, applied forward to what was about to happen. Stay with me. Because what happens next is not just the story of a disaster. It is the most precise and documented example in American engineering history of exactly how an organization decides to ignore the one person in the room who is right. 6 months before this night, on July 31, 1985, Roger Boisjoly had submitted a formal memo to his supervisors at Morton Thiokol. The memo was specific, technical, and unambiguous. He described the erosion he had observed in the O-ring seals on field joints from previous flights. He described the mechanism by which cold temperatures reduced the resilience of the rubber, slowing its ability to seat properly and create the gas-tight seal that separated the controlled explosion inside the booster from the vehicle, carrying 7 human beings. He wrote, in language that left no room for misinterpretation, that if the erosion trend continued and was not addressed, it was a matter of time before the result was a catastrophic failure. He used the phrase, catastrophic failure. He recommended a complete halt to launches until the joint design was corrected. The memo was marked, company private. It was not forwarded to NASA management. It was filed. And Roger Boisjoly continued coming to work every day at Morton Thiokol, continuing to study the joints, continuing to document the erosion, continuing to raise concerns through internal channels that were quietly absorbing his warnings and producing no changes to the launch schedule. Now here is the part of this story that most people who know about Challenger have never been told. Because the standard account of what happened focuses on the night of January 27th and the decision that was made in those hours. But the decision that killed 7 people was not made on January 27th, 1986. It was made in a series of smaller decisions over the preceding 18 months. Each one individually defensible. Each one individually reasonable within the context of organizational pressure and schedule demands and the specific way that large institutions process information that threatens their operational momentum. Roger Boisjoly was not the only person who knew about the O-ring problem. The erosion had been observed and documented across multiple flights going back years. Engineers at NASA and at Morton Thiokol had been aware of the issue. It had been discussed in meetings. It had been classified as an acceptable risk. An acceptable risk. That phrase. Those two words sitting next to each other in official documentation, while the rubber seals on the field joints continued to erode with each successive flight. The mechanism worked like this. The solid rocket boosters that attached to the sides of the Space Shuttle external tank were assembled in sections. The sections were joined by field joints, connections between the cylindrical segments of the booster. Those joints were sealed using two rubber O-rings, a primary and a secondary. When the booster ignited and internal pressure spiked in the fraction of a second after ignition, the primary O-ring was supposed to seat itself against the metal surface, creating a gas-tight seal that prevented the superheated combustion gases from escaping through the joint. The problem was timing. The metal housing of the joint flexed slightly under the pressure spike. In the milliseconds between ignition and the moment the primary O-ring needed to seat, there was a gap. If the O-ring was resilient enough, it moved fast enough to close the gap before the gas could get through. If it was not resilient enough, if it was cold, if the rubber had stiffened below its designed operating temperature, it moved too slowly, and the gas got through. Roger Boisjoly understood this mechanism with the precision of a man who had spent years thinking about nothing else. He understood that the resilience of the rubber was directly and measurably related to temperature. He understood that the flights which had shown the most significant O-ring erosion had been the coldest flights. He understood that the joint design had a fundamental flaw that had been known for years, and that the only reason every previous flight had not ended the way January 28th ended was that the flights had been warm enough, or that the erosion had been caught before it burned completely through, or simply that they had gotten lucky. He understood all of this. He documented it, he submitted it through proper channels, he raised it in meetings. He put his name on written warnings that used the word catastrophic. And on the night of January 27th, he stood in front of a teleconference screen in Huntsville, Alabama, and presented it one more time. The NASA manager on the line said something that has since become one of the most studied sentences in the history of engineering disasters. When the Morton Thiokol engineers pushed back against the launch recommendation, when they made clear that the data did not support a launch at the forecast temperature, the NASA manager said, quote, "My God, Thiokol, when do you want me to launch? Next April?" That sentence is worth sitting with for a moment. It is not a technical argument. It is not a counter to the engineering data. It is a statement of institutional frustration directed at the people responsible for providing the technical justification for a schedule-driven decision. It is pressure, applied directly to the people in the room, in the presence of the engineers who had raised the safety concerns, as a signal about what the organization needed. And it worked. Morton Thiokol management asked for a 5-minute caucus. They muted the phone line. They asked the engineers to leave the room, and they made a management decision rather than an engineering decision. The vice president of engineering at Morton Thiokol, a man named Bob Lund, was told by his superior to take off his engineering hat and put on his management hat. Those are the exact words. "Put on your management hat." He did. When the phone line reopened, Morton Thiokol approved the launch. Roger Boisjoly was in the room. He knew what had happened. He and a colleague, Arnie Thompson, had continued arguing until the moment the caucus was called. After the decision was made, Boisjoly signed none of the approval documentation. He returned to his seat and sat in silence while the teleconference concluded. He knew what was going to happen. The following morning, January 28, 1986, at 11:38 Eastern Standard Time, Space Shuttle Challenger lifted off from Launch Complex 39B at Kennedy Space Center. The temperature at the launch site was 36 degrees Fahrenheit, the coldest launch in the history of the Space Shuttle program. At 73 seconds after launch, at an altitude of approximately 46,000 feet, traveling at nearly twice the speed of sound, the primary O-ring seal on the right solid rocket booster failed. Superheated combustion gases at 5,000 degrees Fahrenheit escaped through the joint. The escaping gas burned through the strut, connecting the booster to the external fuel tank. The booster rotated out of alignment. The external tank ruptured, and the vehicle, traveling at 1,977 miles per hour, was torn apart by aerodynamic forces it was never designed to withstand. The crew cabin separated from the vehicle and continued upward, reaching a peak altitude of approximately 65,000 feet before beginning its descent. It fell for 2 minutes and 45 seconds before impacting the Atlantic Ocean at a speed of over 200 miles per hour. 7 people died. Commander Francis Scobie, pilot Michael Smith, mission specialists Judith Resnick, Ellison Onizuka, and Ronald McNair, payload specialist Gregory Jarvis, and Krista McAuliffe, a high school social studies teacher from Concord, New Hampshire, who had been selected from over 11,000 applicants to be the first civilian in space. Roger Boisjoly watched it on a television monitor in the launch control area. He had known it was going to happen. Now I want to explain something to you about what the investigation that followed actually found. Because the presidential commission that was convened to investigate the disaster, the Rogers Commission, did not find a technical failure. Not primarily. What it found was a management failure, a systematic failure of the information flow within NASA and its contractors, a culture that had normalized risk to the point where documented evidence of a known danger had been reclassified as an acceptable condition, a decision-making structure where schedule pressure and institutional momentum could override the specific technical objections of the engineers who understood the system best. The Rogers Commission found that the O-ring problem had been known to NASA management for years. They found written documentation of the erosion. They found meeting minutes where the issue had been discussed and categorized as an acceptable risk. They found that Roger Boisjoly's July 1985 memo had never been seen by NASA's top management. The memo describing the potential for catastrophic failure, sitting in a Morton Thiokol filing cabinet for 6 months, had never reached the people with the authority to act on it. They found that on the night of January 27th, the engineers who had the data and understood the mechanism were overruled by managers who were responding to schedule pressure from an agency that had tied its institutional credibility to a launch timetable. They found that the system had been designed in a way that made it possible for the one person with the right information, with the documented evidence, with the formal written warning already on file, to be sitting in a room watching a decision be made that he knew was wrong, and to have no mechanism available to him to stop it. Now let me tell you what happened to Roger Boisjoly after the disaster. He cooperated fully with the Rogers Commission. He provided them with his documentation, his memos, his internal communications, his analysis of the O-ring behavior. He told them exactly what had happened in the teleconference on the night of January 27th. He described the moment when the engineers were asked to leave the room. He described the pressure that was applied to Thiokol management. He described the instruction to put on a management hat. His testimony was damaging to Morton Thiokol. It was damaging to NASA. It was accurate. After his testimony, he was effectively isolated within the company. He was removed from NASA-related projects. His phone calls went unreturned. Engineers who had been colleagues for years began to avoid him in the hallways. He developed severe stress-related health problems. He took a medical leave of absence that extended indefinitely. He never returned to work at Morton Thiokol. Roger Boisjoly spent the rest of his working life as a forensic engineering consultant and as a speaker and educator on the subjects of engineering ethics, organizational communication, and the specific ways that institutions suppress technical warnings when those warnings create inconvenient schedule pressure. He spoke at universities. He spoke at professional engineering organizations. He talked about what it feels like to be the person in the room with the right data and the wrong hat. He died in 2012 at the age of 73. Now I want to give you the forensic reconstruction, the complete sequence of decisions that produced this outcome. The O-ring joint design was identified as a potential problem during the original qualification testing for the Space Shuttle solid rocket boosters. The manufacturer, Thiokol, was aware of the design limitations. NASA was aware. The joint was certified for flight with the understanding that the design would be improved in subsequent versions. The subsequent versions were not implemented before flights began. Erosion was first observed on the second Space Shuttle flight STS-2 in November 1981. The O-ring on the nozzle joint showed evidence of hot gas bypass. The observation was documented. It was classified as an anomaly. Flight continued. Over the following 4 years, O-ring erosion was observed on multiple additional flights. The data was compiled. The pattern was visible to anyone who looked at the compiled data. The correlation between cold temperature and erosion was present in the numbers. The data was not compiled in a way that made the temperature correlation visible to the decision-makers who were approving launches. It was presented flight by flight, rather than as a trend across flights. When you look at flight-by-flight data, and each individual flight is within acceptable parameters, the accumulating pattern of a correlation across flights is not visible. Roger Boisjoly and other engineers at Thiokol saw the pattern because they were looking at the full data set. The management and agency officials approving flights were looking at individual flight data. This is not a conspiracy. This is an information architecture problem. The system was not designed to make the trend visible, and because the trend was not visible, the accumulating risk was not visible. And because the risk was not visible, the schedule continued. In July 1985, Boisjoly's memo introduced a new variable. He was not just reporting erosion, he was predicting catastrophic failure and recommending a launch halt. This escalated the issue from an engineering anomaly to a program-threatening problem. A memo recommending a program halt carries organizational consequences. It threatens schedules. It threatens funding. It threatens relationships with NASA customers. The memo was managed internally. It was not forwarded up the chain. In the fall of 1985, NASA conducted an internal review of the Joint SEAL problem. The review acknowledged the concern. It did not result in a launch halt. It resulted in a classification of the issue as an acceptable risk with a commitment to address the joint design in a future version of the hardware. Acceptable risk, future version. Schedule continues. On January 27, 1986, for the first time in the history of the program, the temperature concern was raised directly and explicitly in the context of a specific launch decision. Boisjoly and his colleagues made the clearest possible technical case against the launch. They had data, they had photographs, they had the July memo. They had the correlation mapped across every cold weather flight in program history. They were overruled. Now here's the counterfactual that engineering historians and safety researchers have studied for nearly 4 decades. What happens if the July 1985 memo is forwarded to NASA top management? The memo described a known flaw in a critical system in language that recommended a complete program halt. If that memo had reached the administrator of NASA, or the associate administrator for spaceflight, or any senior official with the authority and the institutional incentive to take it seriously, what is the probability that the joint design would have been corrected before January 1986? The engineers who have studied this question professionally do not argue that the answer is 0. What happens if the data from previous flights is compiled and presented as a temperature correlation rather than as individual flight anomalies? The Rogers Commission found that when the full data set was mapped with temperature on one axis and O-ring erosion severity on the other, the correlation was visually clear. It was unmistakable. If that chart had existed and been in front of the people approving the January 28th launch, the probability that the launch would have been approved at 36 degrees Fahrenheit is a question that serious people consider seriously. What happens if the engineers in the room on the night of January 27th had not been asked to leave? Roger Boisjoly was arguing directly against the launch with data in his hands. His colleague Arnie Thompson was drawing diagrams at the conference table trying to show the managers what was going to happen to the rubber. If the management caucus had not happened, if the argument had continued, if the engineers had not been removed from the room while the approval decision was made, is there a world where the outcome is different? These are not questions without answers. They are questions with probable answers that the people who study organizational failure in high-stakes engineering environments have been working on since 1986. The probable answers are not reassuring. Now I want to tell you why this story matters beyond Challenger. Because the Challenger disaster is not an anomaly. It is a template, a documented, investigated, publicly available template for the specific mechanism by which organizations with genuine technical expertise and genuine institutional commitment to safety nonetheless produce catastrophic failures. The mechanism is not incompetence. It is not malice. It is not negligence in the simple sense. The mechanism is the systematic suppression of technical warnings by organizational structures that are optimized for schedule and output, rather than for the accurate transmission of safety-critical information to the people with the authority to act on it. Roger Boisjoly did everything right. He identified a problem, he documented it, he submitted it through proper channels, he escalated it formally, he raised it in meetings, he raised it one final time on the night before the launch with the clearest possible data available to him. The system absorbed every warning he produced and continued moving forward. The system was not designed to stop. It was designed to continue. And Roger Boisjoly, with all his expertise and all his documentation and all his moral clarity about what was going to happen, was not a part of the system that had the power to make it stop. He was a part of the system that had the power to generate warnings that the other part of the system was not required to act on. This is not a historical problem. This is a structural problem, and it appears with variations in the specific technical details in every organization that has produced a large-scale engineering disaster in the decades since Challenger. It appeared at Columbia in 2003. It appeared at the Deepwater Horizon in 2010. It appeared in the Boeing 737 MAX certification process. The engineers with the technical knowledge and the documentation are in the room. The organizational pressure to continue is also in the room. And the structural question, the question that Roger Boisjoly's story makes impossible to avoid, is whether the system is designed in a way that allows the first group to stop the second. In most of the cases we know about, it is not. There is one more thing about Roger Boisjoly that I want you to know. After the disaster, after his testimony, after the isolation and the health problems and the end of his career at Morton Thiokol, he continued talking. For decades, he went to engineering schools and business schools and professional organizations, and he talked about what had happened, not as a cautionary tale in the abstract sense, but as a specific account of a specific night in which a specific decision was made by people who knew what they were doing and chose to do it anyway. He was not angry in the way you might expect a man to be angry, who had been right and ignored and then proven catastrophically right in the worst possible way. He was something quieter than angry. He had the specific quality of a person who has processed a thing completely and arrived at a form of understanding that does not require the anger anymore. He said in one interview late in his life that he thought about the 7 people on Challenger often, not about the failure, not about the politics or the organizational dynamics or the management decisions, about the people, about what it meant that they had trusted the system, that they had climbed into that vehicle with the understanding that the system had verified it was safe to do so, that the system's job was to be worthy of that trust, and he had tried to make it worthy. That is the weight that the person in the room with the right data carries when the system does not listen. The next time someone in a meeting raises a concern that is inconvenient, that threatens a schedule, that creates pressure at the wrong moment, that sounds like an obstacle rather than a contribution. Remember what it costs when the person with the right data is treated as the problem rather than as the solution. Roger Boisjoly submitted his memo on July 31, 1985. He described a catastrophic failure waiting to happen. He was right about everything. He was right about the mechanism. He was right about the temperature correlation. He was right about what would happen if nothing changed. Nothing changed. And 73 seconds after launch on January 28, 1986, everything he had predicted came true over the Atlantic Ocean at 46,000 feet. Tell me in the comments, have you ever been the person in the room with the right information and the wrong hat? Have you ever submitted the memo that nobody forwarded? Have you ever watched a decision be made that you knew was wrong and had no mechanism available to stop it? Your story matters. And the engineers watching this right now, some of them in that exact position in their organizations today, need to hear it. I will see you in the next one.